So in video 2, for logarithmic functions, we're going to look at how to graph a transformed logarithmic function, and we're going to look at how to identify the domain and range of a transformed logarithmic function. So really we're just going to apply the same function transformations that we learned earlier in the semester. We're just going to apply them to a toolbox function that is a logarithmic function. So the first thing to do when you're doing this is to look at the logarithmic function that you're given. In this case, g of x equals negative log base 2 of negative x minus 2 plus 3. And you want to identify from that what the toolbox function is. And in this case, the toolbox function is the function log base 2 of x, the simplest possible base 2 log function that you can possibly have. And then you want to do the same thing that we've been doing all semester. You want to find a couple key lattice points on this function, and you want to identify the vertical asymptote for the function. That's maybe the thing that's a little bit new that we haven't dealt with before. So the fortunate thing with the log functions is it's pretty easy to come up with nice points. You want to plug in key points that are adapted specifically to the base that you're working with. So for example, 1 is always a good point to plug in, or sorry, a good input value to plug into a log function, because for every log function that you get, you can generate a 1 by taking your base and raising it to the 0th power. And what we want to recognize or remember with log functions is that the logarithm is the exponent that you raise the base to get the number that you put in. So if 1 is 2 to the 0, 2 to the 0 equals 1, then the output to the log function is going to be the exponent every time. And this gives you an ordered pair on the graph. If when you input 1, which is the same as 2 to the 0, the output is the exponent. So the other simple point to get on the graph when you're working with a base is to input the base into the function. This is going to be the second simplest point to get. And the reason it's easy is because 2 is the same as 2 to the 1, and a logarithm always outputs the exponent you raise the base to get the input. So clearly the exponent is 1. 1 is the exponent I raised 2 to get 2 to the first, or 2. So that generates another point on the graph. Input 2, output the exponent of 1. We could even do log base 2 of 4 as a good choice, because 4 is the same as 2 squared, and the logarithm is just going to output this exponent, and we would get a lattice point, input of 4, and the logarithm outputs the exponent you would raise 2 to get the input of 4. So this generates nice lattice points. Here's the point 1, 0 right here. Here's the point 2, 1. Here's another point 4, 2. I don't need to use that point. I think in general, Alex asked you to input or to generate 2 points on the graph plus the vertical asymptote in order to graph a function. But I could generate kind of infinitely many nice points by just putting in nice values for my inputs that play well with the base that I have. Powers of the base will give me nice exponent outputs. The toolbox function for every logarithm base b is the y-axis, or the equation x equals 0, which I've already dashed in here as a red line. So this is going to be the vertical asymptote for every logarithm base b. That is a toolbox function. So then once you have those key points on the graph, you want to go up and look at your transform function g of x, and you just say, hey, what transformations have been applied to the toolbox function to generate this new function? And we walk through this the same way that we've walked through it the entire semester. First, we look at it and say, has there been a horizontal shift? Yes, I'm subtracting 2 from the input variable. This is going to move the graph 2 to the right. And then you're going to look and see, is there a reflection being applied to the input variable? Yes. There's a negation on the input variable, which is going to reflect over the y-axis. Reflect over y-axis. No stretch going on out here, but there is a negation on the log function, which is a reflection over the x-axis. This is an x-axis reflection. And 4, I'm adding 3 to the toolbox function, which is going to move the graph up 3. So what you can do then is go back to your lattice points. I'm not going to use this one because we don't need it. We just need 2 points. Here's 1, here's 2. And let's just sequentially apply the transformations to those points. So here's the point 2, 1. Transformation number 1 says move it 2 places to the right. Transformation 2 says reflect over the y-axis, which is going to take x equal to 4 and bounce it over to x equal to -4. Then transformation number 3 says reflect this point right here over the x-axis. So y equal to 1 will bounce down to y equals -1. And then the last transformation says move this point here up 1, 2, 3, and you'll land on the graph. So here's the point -4, output 2. And then we can grab this other lattice point or key point on the graph and do the same thing. We can say, what's the first transformation? 2 to the right. Transformation number 2, reflect over the y-axis. X equal 3 becomes x equal -3. X-axis reflection, y equals 0 becomes y equal the opposite of 0. Y is still equal to 0. Now move up 3 units. So from here I move up 1, 2, 3, and I wind up as a lattice point on the transformed graph. So I'm at -3, 3. And then the last step is actually to take and transform the vertical asymptote. Well, the vertical asymptote is the line x equals 0. So only horizontal transformations will impact the vertical asymptote because the equation is an x equals equation. And horizontal transformations impact the x variables or the input variables. Vertical transformations have no impact on x equal things. So this starts out here at x equals 0, and then it says move 2 to the right. So we move x equals 0, 2 to the right. He's going to wind up right here at x equal to 2. When we move x equal to 0, 2 to the right, he becomes x equal to 2. And then when we reflect x equal to 2 over the y-axis, x equal to 2 becomes x equal to the opposite of 2, or x equals -2. And so now we have our new vertical asymptote at x equal -2 that we got by just applying the horizontal transformations to the toolbox function's vertical asymptote. And then finally you just draw through those 2 points and sweep up along your vertical axis. Of course, I am a horrible graph drawing person, so I went ahead and let GeoGebra draw the graph in ahead of time, with the understanding that what is important is how we're landing the lattice points on that new transformed graph and how we're transforming the vertical asymptote. Finally, we're asked to determine domain and range of the transformed function. And again, it suffices to initially think about the toolbox function. We know that the domain of the toolbox function, which is right here, is x can't get to 0, but he approaches 0, right? We've got an arrow going down along the vertical asymptote. The x values are approaching that vertical asymptote but never getting to it. So we have an open interval, and there's an arrow here indicating the graph goes infinitely far to the right and infinitely far upwards. So we know x is going off to infinity. The range is y is going from -infinity to +infinity. And I should have an is an element of that interval right there, is an element of the interval from negative infinity to infinity. And the key is that only horizontal transformations can impact the x variables. So only the horizontal transformations that we applied to the toolbox function are going to have any impact on the domain, and only vertical transformations can impact the range or the y values, because the outputs are graphed on the vertical axis. So vertical transformations impact the range, which is graphed on the vertical axis. Horizontal transformations impact the domain, which is graphed as x values on the horizontal axis. So all we need to do is recognize that no vertical transformation of just moving things up or down or stretching is going to impact a range that is going from negative infinity to infinity. So on this transform function, with the arrow going forever in each direction, we see that we're going infinitely far up, and the arrow here indicates we're going infinitely far down. We have a domain and a range. The range, where the y values are going, are still going to be going from negative infinity to infinity. No simple vertical transformation that's a stretch or translation is going to change that. But the horizontal transformations, 2 to the right and reflect over the y-axis, are going to impact the domain. The domain wasn't going from negative infinity to infinity. So it is going to have an impact on this. And what we can do is look at the domain of the toolbox function and say, how does each transformation impact those domain values? Well, the first says move all the x values 2 to the right. So if we do that, if we move these 2 to the right, we'll get 0 plus 2. We would get a new domain. Now x would be going from 0 plus 2 is 2. Move 0, 2 to the right. Infinity plus 2. Move infinity 2 to the right. Well, infinity plus 2 is, you get a calculator. No, it's infinity still. That didn't impact that. But then it says reflect the x values over the y-axis. So when you reflect those x values, you're going to get a negation on the 2 and a negation on the infinity. But you can't put negative 2 before negative infinity. You want the numbers in ascending order, so we need to write negative infinity to negative 2. So the domain ultimately is x is an element of negative infinity to negative 2 based on how the horizontal transformations impacted the domain of the original toolbox function. And the graphical evidence backs this up. We see that we have x's approaching negative 2 but never getting there. There's the vertical asymptote, and the x's, because of the arrow right here, are going off to negative infinity. So we'll walk through one more example using a logarithm with a different base, but the principles are going to be the same. The concepts are the same. You look at the logarithm that you have that's a transformation of some toolbox function. First, identify the toolbox function by identifying what the base is that you're working with. Log base 3. So my toolbox function is the log base 3 of x. And then, because we're going to be transforming a toolbox function to create our transform function, we want to generate some key points on it. And again, this input 1, output 0 is on every single logarithmic function is on every single logarithmic function that is a toolbox function. Every function of the form log base b of x has the point 1, 0 on it. And we can justify that just like we did before by putting log base 3 of 1 equals, well, we know that if we take the base 3 and raise it to the 0th power, that will give us the 1. And the logarithm is the exponent that you need to raise 3 to get the 1. So the logarithm is going to be the exponent. Logarithms are exponents. That's what they are. And you get the nice ordered pair, input 1, output the exponent 0. And we can get the other lattice point the same way as we did before. We can say, hey, take the base and put the base as the input into the function, because that generates a nice lattice point, because 3 is the same as 3 to the first, and logarithms are the exponents, and that generates the ordered pair input 3, output 1. Once we've generated our lattice points, we need to draw in our vertical asymptote, but the vertical asymptote for every toolbox function that is a logarithm is the line x equals 0. And then we want to look at the function that we have, g of x, and say what transformations have been applied to the toolbox function to generate this new function. Here we see we're adding 1 to the input variable, so we move the graph 1 to the left. So translation 1 to the left. No negation on the input variable, so no y-axis reflection, but there is a negation on the function itself, which generates an x-axis reflection. And then number 3, we see that we subtract 2, which moves the graph down 2 units. So we can do the same thing that we did on the previous slide. We can just look at the lattice points and sequentially apply the transformations to them. What happens to this point? It gets moved. Transformation 1 says move it 1 to the left. He's going to land here. And then it says reflect him in the x-axis, so x equal to 2. Sorry, not x, y equal to 1, so x-axis reflection. Y equal to 1 is going to become y equal to -1, so he's going to get reflected down to here. So we moved him over 1, reflected him to here, and then the final transformation in step 3 says move him down 1, 2 units, and we wind up at the lattice point to -3. Now we can apply our transformation sequentially to this point. This says transformation number 1 says move 1 to the left, reflect in the x-axis, so y equals 0 becomes y equal the opposite of 0 is still 0. We're stuck on the x-axis. And transformation number 3 says move down 1, 2 units. We wind up with this lattice point right here, which is 0, -2, right on the axis. And then finally, transform your vertical asymptote, which is an x equal kind of thing. So the vertical transformation, the down 2 is a vertical transformation, will not impact the location of the vertical asymptote. And the x-axis reflection is a vertical transformation and will not impact the location of the vertical asymptote. But the horizontal transformation, move 1 to the left, will. So this says take x equals 0 and move it 1 to the left. So x equals 0 will become x equal to -1. There's the vertical asymptote. And even though it looks like the graph is touching it, it's not. It just gets infinitely close to it, and it's impossible for the computer to make it visually apparent to you that they don't touch. The graph doesn't touch its vertical asymptote. And then the final step is draw in the graph by drawing through your 2 points and sweeping up along your asymptote. And again, because of my poor graph drawing abilities, I went ahead and let GeoGebra draw that in for me ahead of time. And then we're asked to identify domain and range. But it's the same thing as we had before. The toolbox function, what's his domain and range? Well, the domain is always for the toolbox function 0 to infinity. The range is always for the toolbox function negative infinity to infinity. So for the transformed function right here, x is going to be different because we've had a horizontal transformation, but the y is still going to be negative infinity to infinity. But x will the domain will have been transformed based on the transformation that applied here. And this transformation said, hey, move all the x values 1 to the left. So if we move this 1 to the left, we're going to get 0 minus 1 is -1, still going to infinity because infinity minus 1 is still pretty infinite.